So good afternoon. So the topic what I'm going to discuss now today is quarter wave transformer, slotted waveguides, and the conjugate matching. So what is quarter wave transformer? A quarter wave transformer is a simple impedance transformer which is commonly used in the impedance matching in order to minimize the energy which is reflected when the transmission line is connected to a load. So if you see this structure, you have a ZL or RL, and we have one Z0, that is a characteristic impedance of the transmission line. So between the ZL and Z0, we are going to introduce one matching circuit. That matching circuit, I'm calling it by the name as quarter wave transformer. Why it is called as a quarter wave transformer is because this matching circuit is nothing but basically a transmission line of length lambda by 4. Okay, so I'm going to just use a transmission line whose length is lambda by 4 and whose impedance is Z1. This line only will act as a matching circuit between the RL and Z0. So the quarter wave transformer is not basically nothing but a lambda by 4 transmission line. It is using a transmission line with different characteristic impedance with the length of 1/4 of the guided wavelength to match a line to a load. The theory only has been explained here. So now if I see here, the quarter wave line or a line is nothing but an impedance network. It's basically an impedance matching network. The formula for the input impedance or a lambda by 4 log. The formula for the input impedance of a transmission line is, we know this formula, isn't it? Zn is nothing but Zn of minus L is nothing but Z0 into Za. Za can be nothing. Za is nothing but the Zr or Zl. So the load impedance is named here as Za plus J into Z0 tan of beta L divided by Z0 plus J Za tan of beta L. So now I am telling that here my length of the transmission line what I am going to use between the ZL and the Z0 is nothing but lambda by 4. So I'll substitute Zn of L is equal to lambda by 4, which is Z0 into Za plus J Z0. I'll substitute this, and finally I'll be getting my Zn as Z0 square by Za. So Zn is nothing but the input impedance, that will be Zn is nothing but the input impedance of the quarter wave transformer line, that is nothing but the characteristic impedance square by Za. So I can even find out what is Za. Za will be written as Z0 square Za. You can find out what is Za. Zl. Zl will be nothing but you bring here this down, so Z0 square by Zn will be Zl. So now if I go for one example, we are going to match a load with an impedance Za is equal to 100 ohm to be 50 ohms. So your Zn is 50 ohm and Zl is 100 ohm. And what is the transmission line length? What I'm going to use here is lambda by 4. So you know already Zn is equal to lambda by 4. Zn at L is equal to lambda by 4 is equal to Z0 square by Z. So 50 is equal to Z0 square by 100. So Z0 I can find it as root of 50 into 100. 100 is nothing but your load impedance and 50 is nothing but the input impedance of the quarter wave transmission line. And now I have to find out what is the characteristic impedance of the quarter wave transmission line. So that is nothing but 70.71. Okay. So now this technique is commonly used in the patch antennas. So circuits are printed as shown in the figure. A 50 ohm microstrip transmission line is matched to a patch antenna via a quarter wave transmission line. So a 50 ohm transmission line is matched to the patch antenna. So here if you see, this is nothing but your transmission line of lambda by 4 and this is of 50 ohm. Okay, is matched to a patch antenna. Impedance typically 200 ohms or more via a quarter wave length microstrip transmission line with the characteristic impedance chosen to match the load. So because a quarter wave transmission line is only a quarter wavelength at single frequency, this is called as a this is a narrowband matching network. So if I see the quarter wave transmission line, if I use and design any matching circuit, that is going to give me a narrowband matching response. Okay, so now this there are two type of transmission lines, short circuited and open circuited. So short circuited lines are nothing but I'm going to load in the ZL or the ZL or ZR will be a short circuited load. So I'm going to replace the output impedance or the load impedance with a short circuited load here, or I'm going to short circuit the end, because which I can call that line as short circuited line. So we know the general formula for ZL. The input impedance or input admittance 1 by Z for a short circuited line is given by Zn is equal to J into Z naught tan beta L, and Yin is minus J into cot beta L by Z naught. One is the impedance, other one is the admittance. Substituting the uh, condition of ZL as infinity, we can obtain short circuited the ZL will be 0, whereas open circuited ZL will be infinity. So there is a problem here which will be helping us to solve how to find out the length of the stub what I have to introduce here in order to match two different impedances. That to a short circuited transmission line, I am going to use it here. This short circuited transmission line will try to match the input impedance and the output impedance. So using a short circuited transmission line, reactive impedance is added to the circuit. Okay, an antenna which has an impedance of ZA is equal to 50 minus J10. Using a short circuited transmission line, Z0 is 50 and VP is C in parallel with the antenna. Transform the input impedance to the entirely real. I want to now convert the input impedance also to be real. Okay, so you find what is YA. So YA will be 1 by ZA. So 1 by 50 minus J star 10. So YA is equal to 0.0192 plus J star 0.0038. Now we are going to add a reactance in parallel with the value of YA. Okay, in order to make this YA a real term, the admittance will be entirely real. So the impedance will be entirely real for the length of the transmission line. So now the YA is found by, so how do I find this Yin? Yin, you have a formula here. Yin is minus J into cot beta L by Z naught, which is nothing but minus J 0.0038. So find cot beta L from this. Beta L is equal to 2 pi by lambda into L. So this is going to give us beta L as 1.383, whereas L is equal to 0.22 lambda. So if a short circuited transmission line of length 0.22 wavelengths is added in parallel with the load, then the admittance will become entirely real and given by Yin is equal to 0.0192. So hence the input impedance Zn will be 1 by Yin, that is nothing but 52 ohms. So now I try to convert ZA as well as Zn as well as Z0 all to be of 50 ohms or close to 52 ohms. So which is making the whole circuit as a real circuit. Okay. So by introducing a short circuited transmission line close to the output load, I'll try to at a certain length, I will try to cancel the admittance part, so that not the admittance part, the reactance part of the admittance, so the admittance value will become totally real. So now if I come to open circuited transmission lines, if a transmission line is terminated in an open circuit, then ZA will be infinity. Then the impedance of the line will be founded with two formulas. Zn is equal to minus J Z naught cot beta L, and Yin is J tan beta L by Z naught. So from these two equations, finally we can go for finding the open circuit and short circuited impedances. This open circuited and short circuited transmission lines can be used as a substitutes for inductors and capacitors whenever we want to add some reactance. So Z0 can be ZOC and ZSC can be written like this. ZSC or ZNSC can be written as J Z0 tan beta L, and ZOC can be written as minus J Z0 cot beta L. So how do I find Z0 from this? Z0 is nothing but square root of ZSC and ZOC. So now we'll go to the next topic, slot line section. So slot line section in a microwave component is a microwave component. It is used to find the VSWR ratios. Okay, so this was the very old equipment what we have from the beginning. It is one important equipment in the or important component in the microwave test bench, which is used to find VSWR characteristic impedance. Okay, and even the lambda G wavelength, guide wavelength, all those things can be found out by this slot line section. The slot line section will look like this thing what is shown in the pictures. This is one slot line section, this is another slot line section. And before the time network analyzers were started coming, no, before the time, this was the earlier equipment which has been used to find the standing wave ratios. So the slot line section consists of a slotted section of transmission line where the measurement has to be done. It will have one traveling wave probe carriage. This is nothing but the traveling probe carriage to let the probe get connected wherever necessary, and the facility for attaching and detaching the instrument. This probe can be removed easily or get connected back, and through this probe, an output will be taken, and we'll be observing the output in CRO. By moving this black color one, there is one knob kind of thing, no, or this mobile probe. By moving this black color knob kind of thing, front and back on the in the axis x-axis scale, you can find out the V minimas and maxima positions of the voltage standing waves formed inside the slot line section. A mobile probe connected to the detective. Here from this probe, I'll connect this. A mobile probe connected to a crystal detector is inserted into the slot of the waveguide. You can connect this to a crystal detector. Okay, that crystal detector will detect the output from the microwave frequency to the normal frequency range of 1 kilohertz, which can be observed in the CRO. Okay. So what are all the applications of slaughter section? If you see, it is used to measure the unknown frequency by measuring the distance between the voltage peaks and noting the distances 1 by 2 wavelength, and measure VSWR, measure characteristic impedance, and I can find the unknown frequency. I can find the wavelength also, guide wavelength, okay, guide frequency, guide wavelength. All this can be obtained with this. Okay, so next we'll go for the conjugate matching. This conjugate matching I'll be explaining in the next video, because there are some derivations to be done for the conjugate matching. So I think this is clear about what we discussed now. We discussed about the type of transmission lines, short circuited and open circuited, and the quarter wave transmission line. Okay, and then we discussed about the slotted section. Thank you.